Let us now introduce the so-called forward-backward method. This method is also called the proximal gradient method. Which is fairly self-explanatory when you see what this method looks like. Just to remind you, we have a function f, which is convex differentiable, and gradient f, the function of course maps to R, and the gradient maps to H, and the gradient should be L Lipschitz. So Lipschitz continues with constant L. And the function g is assumed, so takes values in our bar and is assumed to be proper, convex, and lower semi-continuous. And we assume that we are able to evaluate in some way or another, like we know an explicit formula, for example, of the proximal points of G. Okay, and then we discussed optimality conditions for the setting minimize f plus g. And one of these optimality conditions was that we wanted to find a point x which satisfies the equation x equals proximal gamma g of x minus gradient f of x. Okay, and the proximal method just takes this equation and adds an index n to all the x's on the right-hand side and adds an index n plus 1 to the index x to the x on the left-hand side. And this gives us an iteration, so it's like a recursive formula which defines xn, the sequence xn, whenever you are given a starting point x0 in h. And what you also need to have is some kind of step length gamma, which should of course be positive, and this gamma goes in here and here, and I've forgotten it in front of the gradient, of course, but I got it right in the last video. So what this does is it takes some kind of a gradient step, like in the subgradient method, with respect to f, and it takes the proximal point with respect to g. And of course, we have seen that whenever xn plus 1 is xn, then we have a solution to our problem, and these properties are actually equivalent. So we have a solution if and only if. So xn is a solution if and only if xn plus 1 equals this expression equals xn. Okay, and we should also discuss what we are given here. We're given like a first order information of f at the point xn because we're using the gradient of f at xn. And we're given some first order information, namely some kind of a subgradient of g at xn plus 1 at the result of the proximal point operator. Okay, and this plays some kind of role in some proofs of for the convergence of this method. In particular, if you were to take the step size gamma variable in each step, which we will not do here. So in this case, if you take gamma n instead of gamma, so that the step size can vary from iteration to iteration, then you would have to take care about this discrepancy between first order information of f at xn and first order information of g at xn plus 1. We will not do this here, but our proof only works for constant step sizes, so we have to again delete this gamma n here. Okay. And I did this because the proof for a constant step size, in my opinion, is more intuitive, and a little bit easier because we can directly use the optimality conditions from the last video. Okay, let's just evaluate which first order information we get. So let's call it inequalities of first order information. So for all x in H, what do we have? So we have the gradient of f at xn. Great. We have some subgradient of g at xn plus 1. And this means that when we apply the inequality for the proximal point, we got something like g of xn plus 1 less or equal than g of x at some arbitrary point. This was what we established in the video about the proximal points. We took the inequality of this. So first we divided by the step size gamma. Then we took the inner product of this expression here, this argument, minus the result. So we got xn. We get xn minus gamma gradient f of xn minus xn plus 1. And the inner product with this result minus the point x, this arbitrarily chosen point. So we get this inner product here. And this is basically the first order information on g, and this gives us an estimation about g of xn plus 1. So an upper bound for this expression, which is valid for all x. Okay. And then we get some information about f. As I said, usually in this iteration we use the information of f at xn, the gradient at xn. But because of the structure, we can just use the information about f at the next iteration. This means we can use the information of f at xn plus 1 by using the gradient of f at xn plus 1. So this means this, as we have established in the video about these functions f with Lipschitz continuous gradient, we can bound this by f of x plus inner product of gradient f at xn plus 1 with inner product with xn plus 1 minus x minus, here we have 1 over 2l, l being the Lipschitz constant, norm of the difference of the gradients here. Okay. So this is basically all we know about our algorithm. We just have transformed all the information we have into some simple inequalities, and from these inequalities we're now going to establish the convergence of this iteration to a minimizer of the sum f plus g. First of all, we want to state the fact that the forward-backward method and in contrast to the subgradient method, as we have seen, is a descent method. As long as we appropriately limit the step size for gamma, and of course gamma has to be positive because otherwise the proximal point is not defined, and should be bounded by 2 over L. L again is this Lipschitz constant here. So the choice of the function g does not have an influence on this bound here, only the choice of the function f. Okay, so what does descent method mean? In our case, the function values, the objective function values, are decreasing. This means that f of xn plus 1 plus g xn plus 1 less or equal than f of xn plus g of xn for all n. Okay. And this is very easy to see from those two inequalities. So the proof for this fact, I don't want to state this as a separate theorem. The proof is, well, we take those two inequalities and add them and set x equal to xn in the previous inequalities and add them. So what we get then is f of xn plus 1 plus g xn plus 1 less or equal than f of xn plus g of xn. And now we have, first of all, I take this inner product without this gradient here. So then we have xn minus xn plus 1, xn plus 1 minus xn, because we replace x by xn. So we actually have minus 1 over gamma times the norm of xn plus 1 minus xn squared, because this is the inner product of this expression, once with plus and once with minus. Then we get minus 1 over gamma times gamma, so nothing, times the gradient of f at xn in the inner product with this right-hand side. But we also add the gradient of f at xn plus 1 in the inner product with the right-hand side. So we get plus gradient of f at xn plus 1 minus gradient of f at xn in the inner product with xn plus 1 minus x. Okay. So we have all these expressions here, and then we have to subtract 1 over 2l gradient f at xn plus 1 minus gradient f at xn. Okay, and I see that I forgot to replace x by xn here, but that's easily corrected. All right, and now we see that we have like basically some kind of quadratic expression, and as you know from like binomial formulas, we can expand this to larger quadratic expression, so that the mixed term between the expressions will be this inner product. What I mean by that is we can take 1 over 2l gradient f of xn plus 1 minus gradient f of, at xn, and we add, or we subtract, because we have minus plus here, L times xn plus 1 minus xn. Okay, then we get, if we use the binomial formula, we get minus 1 over 2l, the norm of this difference here squared, so this expression, plus 2 times 1 over 2l, which is 1 over l, times l, which is like 1, inner product of this difference here with this here. So the mixed term in this expression is exactly this inner product. And the remainder will be, first of all, will be this quadratic expression which we have invented here, so we have to correct this. First of all, we have minus 2 over 2 gamma xn plus norm of xn plus 1 minus xn squared, which is this expression. And then we have invented, so we have an additional minus 1 over 2l times l squared, which is l half, times norm of xn plus 1 minus xn squared. So we have L half of this, and L half is L gamma over 2 gamma. Since we have added this with minus here, we have to correct our mistake by adding this with plus in this line, and this gives us exactly this expression here. And of course we have to add f of xn plus f of gn. Okay, and you see, as long as gamma is less or equal than 2 over L, then 2 minus L over gamma, 2 minus L gamma is greater or equal than 2 minus L times 2 over L. So 2 minus 2, 0. So as long as this is satisfied, then this term, this numerator here is positive. So this term here will be non-negative, actually. So this whole term here will be non-positive. This term, this first term, is also non-positive, and therefore the whole expression will be less or equal than f of xn plus g of xn. Okay, so we see, as long as we choose the step size less or equal than 2 over the Lipschitz constant of f, of the gradient of f, sorry, we get the descent in function values. And we will actually see, as long as you choose gamma in this open interval between 0 and 2 over L, so without the boundary here, that we will get a global convergence to a minimizer of f plus g. And the key to this will be to exploit this inequalities here analogously to the analysis of the subgradient method by inserting some solution, some minimizer here instead of x. So instead of substituting x with xn, we want to substitute x with some minimizer of f plus g. And actually this is very specific for the analysis of convex problems, because in non-convex problems there might be several local minimizers, and it is not easy to just take these inequalities for these. But for convex method, you have always this global convexity property, and therefore this is a good option for the analysis of the convergence of convex optimization methods.